Hello and welcome. Today we're going to look at series and parallel circuits and the rules and the philosophy behind them. So a series circuit is typically one that, firstly, there is no such thing as a series circuit or a parallel circuit. Series connections are when they are in line with each other. Okay, so I can have resistors in series, I can have lamps or bulbs in series, I can even have cells in series. Okay, so a series circuit is actually the wrong word to say. It is either the cells that are in parallel, in series, or the resistors. Now we typically would place resistors in series and call it a series circuit. Okay, so firstly, we don't get a series circuit. It is a circuit where the resistors are in series. So if we have a cell and we have our resistors that are connected in line, series is the Latin word for series means in line, okay, we can see that there is one road traveling for where the current flows. There's one road from the cell to the resistor. Now what I typically tell people is keep your two fingers next to each other, and if your fingers don't have to separate, it is a series circuit. I'll show you what is a parallel circuit in terms of that later. So what are the rules for series circuits? Okay, the rules for series is as follows. Okay, we'll have, let's call this one resistor 1, resistor 2. Okay, or R1 and R2. Okay, as previously described, we see two resistors. Okay, let's swap 1 and 2. We have resistor 1 and resistor 2. Each resistor has its own resistance. It uses a certain amount of potential difference or energy per coulomb, and then it has the current flowing through it. Okay, and as I've described in my other video, there is also now a total resistance. Okay, so there in this simple circuit we've got three resistances. We've got this one, and the sum of them together. Okay, so what are the rules in series? The most important rule is that the total current is the same as the current everywhere. So the current here, 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 all the same. Why? Because there's only one road. Okay, so since there's only one road, all the traffic has to follow the same. So the amount of traffic here, 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 here will be the same. If there's 20 cars per second, 20 cars per second, or 20 electrons per second, whatever you want to, what analogy you want to use, the traffic would be the same because there's only one road. Okay. But one of the most important rules that I've taught you guys in energy or them circuits is the energy given, the joules per second, per coulomb given, must be used by the resistors. So the voltage by the cell, total voltage also called the EMF, is equal to the voltage, if we had to measure here, over the resistor 1, plus the voltage used by resistor 2. Okay, now remember, this is true even if we don't measure it. We don't need a voltmeter to know that there's voltage there. We don't need to have an ammeter here, 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 here to know that it's exactly the same. And last but not least, in series, and this is now, these are basically your junior rules, and what we've learned extra now is that the total resistance is the sum of the two resistors. So in series, we will learn that the resistances add up, okay? The voltage adds up, but the current stays the same. So this is the basic rules for series, and that is the rule how to add up the resistors. Now we will be looking and discussing at the rules for parallel circuits. So once again, guys, the word parallel means in Latin alongside of each other. Okay, so I can put resistors in parallel, I can put cells in parallel, okay, but we typically call a parallel circuit a circuit that has resistors in parallel. Okay, so there are different ways to draw a parallel circuit. You can draw your circuit like this, and this is what I would typically do. Okay, then you can draw your circuit like this. This is what Cambridge likes to do. And then you can also draw the same circuit. Let's do it this way. The sideways doesn't actually matter. All three of these are exactly the same circuit. Okay, why do I say that? Take your two fingers. Okay, let's start here. If I take my two fingers, there's a junction in the road, so they separate and they come together here again. So that means this part has a different amount of charges that flows there per second, or current, than this part, because the current splits up. So if we call that I3, we call this one I2, and we call the blue one I1. And then in this case, I1 splits up into I3 and I2. So let's say there is 20 electrons flowing per second. Okay, 10 of them goes along this road and 10 of them goes along that road. Then we have the current splitting up, and then they come together again here. So from here, together, separated, come back together again. So here, anywhere in blue, we have the total current, but here we have the current separated. Now we can do the same thing for the other two as well. Okay, I can draw the red one here, or I can draw the red one here, and I can draw the green one there, and the green one here. Okay, so all three of them show the blue, which is where the total current goes, and then a junction. So I take my fingers together. Where my fingers have to separate, there is a parallel section. When they come together, it is series again, okay, or a single line. Start together, split up, come back together, and back there. So all three of these are ways of showing parallel. Okay, so let's look at the rules for a parallel circuit. Should have actually kept that one there. So let's just do, I'm gonna do the one that I said Cambridge typically gives you guys, the one that looks like a kind of a block. Okay, 2 blocks. So this is the typical type of parallel circuit that you would see. Let's call it resistor 2, and let's call it resistor 1. Okay, so firstly, what did we learn? We learned that the current in parallel is equal to, okay, so let's call that okay, the total current, or well, let's rather say the total current, which is there, is equal to I1. Let's call that branch I1 and this branch I2. So the total current in the blue is equal to the current in the red plus the current in the green. Okay, and when they come back together again, which is up to there, Okay, those two combine again to form the total current. Current can't be lost. Okay, then in parallel, so these are parallel rules. Okay, so the total amount of energy given by the cell, or otherwise known as the EMF, is equal to the voltage at resistor 1, and it's also equal to the voltage at resistor 2. So if the total current, if each little electron gets 10 joules of energy, some of them are going to pass by this resistor and give all their 10 joules of energy here. The rest of them will pass here and give their 10 joules of energy there. And because the red current doesn't flow past this one anymore, they only see one, so they give all their energy here, and the green current gives all their energy here. So both of these resistors gets the maximum amount of energy, but they only get some of the current. So they don't get all the energy, but only some of the current. In series, they get some of the energy, but all of the current. Parallel, some of the current, all of the energy. Okay, and then resistors in parallel, there is a formula, and this is now the basics, and now we go to what we're learning now, is that the resistance 1 over the total resistance in parallel is equal to 1 over resistor 1 plus 1 over resistor 2. So let's say that's 2 and 3. It would be 1 over 2 plus 1 over 3, and that gives me 3 over 6 plus 2 over 6, and that gives me 5 over 6. But 5 over 6 is not the value of the total resistance. The total resistance is actually that inverted. So the total resistance is 6 over 5. Now that gives me 1.2. What do you notice here with the 1.2? It is smaller than the 2, it's smaller than the 3. So when we add resistances together, the total resistance decreases when we add them in parallel. If we add them in series, the total resistance increases. So when we add them in series or in parallel, the total resistance decreases. Okay. Now, there's an easier way of doing this, and this is a formula that I've developed over the years. Here you have to use fractions, mathematics, get a fraction answer, and then you must remember to swap. And other students struggle to do the fractions if they don't use their calculator, or they forget to swap. So my method in doing this is to simply teach a student the following formula. Now that is mathematically already turning something around, and then you'll get that the total resistance in parallel is 6 over 5. It's 1.2 ohms. So the calculator does all the thinking. You write down the formula. This is not the typical formula in the textbook. Typical formula is 1 over and everything, and then you have to flip it at the end. But this is a mathematical flip. So if I type this into my calculator, I get the answer, and my calculator does the thinking. And that's why scientists are lazy. Okay, so we have our resistance formula. When we add resistors, we have our voltage formula, which says that the voltage is the same. And lastly, we have our current formula, which says that the current splits up and we add the current. Okay, so parallel circuits is called the current divider because the current splits, and series circuit is called the voltage divider because the energy is separated. The same amount of energy from the cell is shared between resistors. Next, we will be looking at two types of mixed circuits. A mixed circuit is typically a circuit that has series and parallel parts. Okay, so what is the thinking behind a circuit like this? Okay, we have series and parallel parts, and what I want to do is I want to calculate the parallel sections, like squishing them together, and then I get a total for the two parallel circuits or resistors, and I still have resistor 1. So the answer of this part is in series with that resistor. Okay, so we have 3 resistors. This one is in series, those ones are in parallel. They use different rules than this one. But if we calculate the total of those two, I get one answer, and that answer is then in series with this one. So I literally squish them together to form one circuit, one resistor. And that answer is in series with this one, and then we treat it as a series circuit from there. The next type of a mixed resistor is when we have 2 resistors in series inside a parallel branch. Now the same thinking applies again. I squish those 2 together and I get an answer for them. And then I will have a resistor, so let's call it RS, the total resistance in series, in parallel with the third resistor. So these two, I use series rules. Once I've added them together to get the total resistance, it's like squishing them together, I get the total in the series, and then I use parallel rules to solve the circuit further along. Okay, so we always, if there's 2 resistors in series, we want to make them one inside a parallel, or on the opposite side, if there's 2 in parallel in a series resistor, we want to first make those 2 one. So we always solve the circuit inside the circuit. So here we've got a series circuit inside a parallel circuit, and the other one we had a parallel circuit inside the series circuit. So here we fix first go to the circuit inside the circuit. Here we go to the circuit inside the circuit, and that is the philosophy or the way that we will approach a mixed circuit question.